Hi, welcome to your lesson on the ambiguous case of the sine rule. And if you see here, the word ambiguous means open to two or more interpretations, so uncertain. We'll be using our calculators. Make sure you're in degree mode. Let's recap where we came from. Recently we saw the sine rule, which is a great rule that allows us to solve for missing parts of a triangle when the triangle is not a right triangle. So by using sine, we are able to find a relationship between angles and sides in non-right triangles. Sine rule looks like this or like this, and it is usually used with only two of these fractions. Important to remember, not all three at once. And the main thing with the sine rule is if you know an angle and the side across from it and another angle and the side across from it, you can make a relationship that has those four parts. One of those four can be unknown and can be solved using the sine rule. Okay, and we looked at a situation like this. Let's say we don't have a diagram. We don't know what a triangle looks like, but we are told things about it. For example, there's an angle of 65, angle of 30, and a side that is 13. And we're asked to find a length. Well, we know there's an angle of 65, an angle of 30 here, and a side of 13. There's no other way to draw this triangle. If we draw a 65-degree angle here and a 30 here next to each other, because that's what this tells us here, basically we're locked into these sides going at these angles to each other. Therefore, the triangle is locked into its shape. Like this angle must be a certain angle. These make 95. This therefore must be 85. So we have a triangle that has a set shape. Once we set two angles, the shape of the triangle is set. And then the sides can change, of course, but the shape is set. So that one we can go on to use the sine rule. We can say, okay, we can make a relationship for these two across from each other and these two and put it all together in the sine rule. Okay, so that's sine rule. But what happens sometimes is this. We have another triangle described to us here. We are told it's ABD, angle B is 35, side AB is 10, and side AD is 6. Let's take a look. So we're going to begin with an angle that's 35. So let's say we have two legs here. We don't know how long they are yet, but we know that there's some angle that is 35. It's locked. That angle is locked in this position. All right, AB is 10. So I'm going to say that my A is here, and I'm going to call this 10. So that's also locked, that length. So this angle is locked, that length is locked. And then AD, if this was triangle ABD, then D would be here. And AD would be the segment connecting those. AD is said to be 6. Okay, so AD 6. Well, it seems like we're okay, right? We have this angle locked, this side locked, and this side here locked. Everything seems okay. Well, it's not okay. Let's take a look. There's a little ambiguity here. So we have, again, this angle locked. This side is AD is 10 locked, just like it is here. But AD here was drawn like this, but here I'm going to draw it like this. It still has a length of 6. So AD could have been like this, or AD could have been like this. Notice we're not breaking the rules of what we're giving. We are keeping the angle locked, we're keeping this side locked, and we're keeping this side locked. It's just that that side has swung in and out. It's at a different angle. So we're not breaking the rules, but now we're unclear. Which triangle is it? This is ambiguous. So if somebody told you to find the measure of angle D, you'd be saying, well, is it this angle, which is an obtuse angle, or is it this one, which is an acute angle? Okay, so this ambiguity happens in a very specific situation. It occurs like in what we see here, when we are given an angle, a side, and then another side, which we say in triangles when we're given parts, we can label them like using the letters A and S. In this case, we have ASS. So the ambiguous case occurs when we have an ASS situation, where we're given an angle, then a side, then a side. And the three possibilities in the ambiguous case are that there's no triangle. It's impossible to create a triangle that has those parts. Or there's only one triangle that looks like that. There's only one setting. Or, like we saw, there are two possible triangles that look like that have those three parts. So again, when we have ASS, we can have any of these occur. So there's ambiguity. Let's look at it on GeoGebra. I have it ready here. Okay, so here we have, again, an angle, a side, and a side. The angle is fixed, the side is fixed, and this side is fixed. Notice here, when we're given 43, 9, and 3, this is a situation where there's no triangle that looks like that possible. It's impossible. We can't have that triangle. But if we made A longer, we could have a triangle that's possible. Let's see. If A is a very specific length, oh, wait, let's make it a little bit shorter. Let's see if I can get it to work. I'm trying to show the situation where there's only one triangle like that. I'm having trouble doing it. Alright, let's see if I can get it to work. Okay, so I paused my recording. I was trying really hard, but I couldn't get it to quite work out. But we're back at the situation where we have this side is not quite long enough, so we can't make a triangle. See, it can't quite reach to there. So we have this angle, this side's not long enough. But if I made this side just slightly longer and it was just the right length, imagine this hanging straight down and making a right triangle. So there would be one triangle possible with those three measures, angle, side, and that exact side that makes a right angle. But if this side's a little longer than that, which I'm going to do now, look what happens. It swings below this line here, and that line is set because we have that angle set at 41. So now, where it draws these two blue lines are the two possible triangles, and that's what we talked about. That if this is this length, it can be that length 14.2 like this, or it can be that length 14.2 like that, because we still have an angle, a side, and then a fixed side in both situations. So we have this obtuse triangle, or we have this bigger acute triangle. All right, so that's really important to see here with the ambiguous case. And here it is sketched out again. In the triangle we were given in, I think, this one here, yeah, 35, 10, and 6. So here's the 35, 10, and 6 triangle we were given. Here's 35-degree angle, here's a side of 10, and then so we have angle, side, side, and here's the side of 6. So the 6 could have even gone like that, and we have those locked in position, or the 6 could have swung out to here, and we have 35, 10, and 6 also. So two triangles, this one, and then the whole one. So if you were solving for angle D, you could have thought, okay, I can set up sine rule. Sine of 35 over 6 equals sine of angle D here over 10. Now when you solve that, sine of D, okay, let's solve this. Punch this in your calculator. Let's see what we get. We're going to have to do inverse sine on that to find the angle. The inverse sine is 72.9. So notice, even though it's ambiguous, we don't know whether we have this triangle where D is actually this angle or this one. It gave us this angle. The calculator will always give us the smaller angle. So it will always give us the angle in the ambiguous case for this one here, for this big triangle. So then it's up to us to take that angle and say, okay, I know that that's one possibility, but I know that this other triangle here is another possibility, so what's this angle? Well, the good thing is there's a really clear relationship between this angle and this one. Let's take a look. If this is 72.9, this triangle here is isosceles because we have that same leg which has been swinging side to side. So that means that angle is also the same. Those angles, base angles, are the same in an isosceles triangle. So if this is 72.9, we know this makes 180. So 180 minus 72.9 is 107.1. So that angle will be 107.1. So our other option for the measure of angle D in the original question was, well, it can be this angle, or this triangle works as well, so it can be this angle. And those angles will always have that 180 relationship. So this one will always be what's called the supplement of this one. Okay, so solve for this one and then recognize it's ambiguous and do 180 minus that one to find this one. All right, so with that in mind, let's see if you can solve this one. Try the same approach. We have an ambiguous case here. Let's see if you can find both possibilities for angle C. And here's all that work. Here's the two triangles. Here's a locked angle of 40, and then a side of AB 15, and then BC is 10. Here's where the 10 is swinging out, and we're locked into those three lengths. It works out. And here's where the 10 is swinging in, and we have 40, 15, and 10. So again, when you set up the sine rule, it will give you the smaller angle. 74.6 is this angle. And now it's your job to do 180 minus that to figure out this possible angle. So here's the 74.6, and here's the other possibility for the other possible triangle. It was ambiguous, but we have two possibilities. Now let's say you did all this, and your sine of C, when you did it in the end here, you did the inverse sine, and you tried to find the angle, and it gave you an error. Well, that would mean you're in the situation where there's no triangle possible. And we saw that as well, right? When the side length is just a little too short, like that. It's swinging, but it cannot create any triangles. That's what you'd be finding if you got an error. If you, however, got an angle of 90 degrees, you would know you found that one single situation where this hung perfectly down and made it just to here and had the 90-degree angle. All right, so that's the ambiguous case. I hope that makes sense. It's a great topic, and it's a great thing to visualize geometrically. And I hope you enjoyed it, and we'll see you soon.